We already know how to integrate, and by integrate I mean anti-differentiate, some fractions. For instance, here's an anti-differentiation problem. Let's anti-differentiate 4x plus 3 dx. And I could do that with a u substitution. We have to choose what u should be equal to. I'll set u equal 4x plus 3, so that du is, what's the derivative of this? It's just 4, and then the differential of u is 4 dx. Now, I don't see a 4 dx in my integrand here, but I can manufacture a 4 dx if I multiply by 1/4 and 4. That's like doing nothing, right? Those cancel, but now I've got a 4 dx in my integrand. So the original anti-differentiation problem is 1/4 of antiderivative of 1 over u du. And I know an antiderivative of 1 over u du, right? It's log of the absolute value of u plus c, and I've got to make sure to include that constant on the outside of 1/4. But I don't want to write down my answer in terms of u. I'd like my answer to be in terms of x, right? I'm asking for an antiderivative of 1 over 4x plus 3, not something in terms of u. So I'll just replace u with what it's equal to. So altogether, I've got 1/4 log of the absolute value of 4x plus 3 plus c. So there's my antiderivative of this fraction. I also know how to anti-differentiate some reciprocals of quadratic polynomials. At least here's a special case. What's the antiderivative of 1 over x squared plus 1 dx? Well, if you remember back, I know a function whose derivative is this. Right? It's the inverse tangent function, arctan. So at least I know how to anti-differentiate the reciprocal of this particular quadratic polynomial. Wonderfully, I can use that special case, the antiderivative of 1 over x squared plus 1, to anti-differentiate the reciprocals of other quadratic polynomials. For example, can we find an antiderivative of 1 over x squared plus 4x plus 7 dx? Can you think of a function whose derivative is this? I can't come up with an antiderivative just off the top of my head, but I've got a trick up my sleeve. The trick is completing the square. What that means is that I'm going to rewrite x squared plus 4x plus 7, and I want it to look more like the example I know, right? The example that I know is this thing. I know that the antiderivative of 1 over something squared plus something. So I try to rewrite this quadratic polynomial so it looks more like that. So I'm going to try to rewrite it so it looks like x plus, something squared plus plus something. The trouble is how to find the blue and the red somethings. Well, let's use some algebra. So I'm going to write this as x plus, instead of just a squiggle, I'll call it a squared plus some other constant b. And if I expand that out, what do I get? Well, I get x squared plus a cross term 2ax plus I got an a squared term and then a b left over that I add on. So I'm trying to make this quadratic polynomial look like this. And the only term that I've got with an x here is this 2a should be 4, right? So let me write that down. So 2a is equal to 4, and that tells me what a is. A should be 2. I'll finish by finding b. So I've got x plus 2 squared plus some b is equal to x squared plus 4x plus 7. X plus 2 squared is x squared plus 4x plus 2 squared, which is 4, plus b is supposed to be equal to this. And that tells me what b had better be, right? I've got 4x and I've got an x squared, and I got 4 plus b is 7. All right, so 4 plus b is 7, so b is 3. Let's summarize. So what I've got here is that x squared plus 4x plus 7 can instead be written as x plus, in this case, 2 squared plus, and then for b, I've got 3. So I've rewritten this quadratic polynomial as a linear term squared plus some constant. Now I'll use that fact in the integration problem. Right, the original integral is 1 over x squared plus 4x plus 7, and instead of doing that integral, I can do the integral of 1 over this equivalent thing, x plus 2 squared plus 3 dx. That still doesn't exactly look like the antiderivative problem that resulted in arctan. Remember, the antiderivative here that gave us arctan x has a plus 1, but the thing we're looking at here has a plus 3. So I can fix that. I can get a constant here. I can factor out something. I'll factor out a third, and then it'll be the integral of 1 over 3 times x plus 2 squared plus 1 dx. Right? This is the same thing as this, because this 3 times a third is just the 1 here that I haven't written, and 3 times plus 1 gives me this plus 3. I'll make a substitution. Now I'll make the substitution. You might think that I could use a substitution where u equals 1/3 x plus 2 squared, but then I'd need an x in the numerator, right? So instead, I'm going to make a slightly different substitution. I'm just going to try to make this look like u squared. So I'll set u to be 1 over the square root of 3 times x plus 2. So now this denominator looks like 1 over u squared plus 1. And in that case, what's du? Well, that means du is 1 over the square root of 3 dx. Now, what does the integral become? Now, you might be concerned that you don't see a 1 over the square root of 3 dx here, but I can manufacture one of those. If I make this into the 1 over the square root of 3, I can put a 1 over the square root of 3 here without affecting anything. Now I've got a du. So this antidifferentiation problem becomes 1 over the square root of 3. The antiderivative of 1 over this here is u squared plus 1, and this 1 over the square root of 3 dx, that is now my du. And that's arctan. So this is 1 over the square root of 3. Antiderivative of this is arctan u plus c. Now I just have to replace that u with its value in terms of x. So this is 1 over the square root of 3 arctan, and u here is this, so I'll write that in here for u, 1 over the square root of 3 times x plus 2 plus c. And now I'm in a position to state a conclusion. The original question was asking for an antiderivative of 1 over x squared plus 4x plus 7, and we've found it. It's 1 over the square root of 3 times arctan, 1 over the square root of 3 times x plus 2 plus some constant. So we've anti-differentiated this reciprocal of this quadratic polynomial. Well, fantastic. And the same trick works in other situations as well. Really, any time you've been handed a quadratic polynomial, but you wish you'd been given something squared plus a number, you should try completing the square.